All right, I'll start it off. And we'll just be going over our slides, right?
Yeah.
Okay. Hello, my name is Michael Vargas, and alongside me is Raya Young and Jordan Martin, and we'll be going over presentation over Hooke's Law. Slide 1.2, introduction topic, Hooke's Law. Hooke's Law was discovered in 1660 by British scientist Robert Hooke, and Hooke's Law describes how elastic objects like springs behave when stretched or compressed. 1.3, introduction relevant fields. Hooke's law can apply to many fields in the science world. Hooke's law is a fundamental principle in physics and engineering that describes the behavior of elastic materials. And here are two relevant fields that Hooke's law can apply to. Number one, mechanical engineering. Hooke's law is crucial in the study of material properties, particularly understanding how objects will behave under stress and strain. Hooke's law is used in the design of springs, suspension systems, and a lot of various mechanical components. Number two, civil engineering. In civil engineering, using Hooke's law helps predict and get a better understanding how buildings, bridges, and other structures will respond to forces and loads, and knowing that will keep the people safe and ensuring structural integrity. Slide 1.4, Introduction Relevant Scientists. In the discovery of Hooke's law, one man created the law. However, some other scientists laid the foundation out and helped in the discovery. Robert Hooke was an English physicist and polymath who first stated that the force required to compress or extend a spring is proportional to the distance it is stretched or compressed. And Sir Isaac Newton is best known for his laws of motion and universal gravitation. However, with Isaac Newton laying down the foundation of understanding forces and motion, really helped Robert Hooke, since understanding forces and motion is very important in Hooke's law. 2.1, Experimental Process Original. Robert Hooke's original experimental process for finding Hooke's law involved observing how springs and other elastic materials responded to applied forces. He meticulously measured the extension or compression of springs and other objects that when subject to increasing forces. By analyzing the relationship between the forces applied and the resulting deformation, he discovered that the extension or compression was directly proportional to the force, as long as the elastic limit of the material was not exceeded. This relationship is known as Hooke's law. Robert's Hooke's setup to the experiment was a spring which he suspended vertically, elastic materials, and weights. He would add weights one by one and then observe how much the spring would stretch or compress in response to additional weight. 2.2, Experimental process difficulties. In Robert Hooke's original experiment that ultimately led to the discovery of Hooke's law. Just like any experiment, there would be some difficulties that Robert had to face, and these are some of those. Number one, Robert Hooke's experiment took place in the 17th century. So basically, none technology and measuring tools he had back then would have meant making precise measurements, and it would have made it difficult for him. Accuracy of knowing how much weight he was applying must have been difficult. Any inaccuracies in the weights would directly impact the results and affect the proportional relationship being investigated. And finally, faulty data. Without modern statistical methods and tools, analyzing data and deriving meaningful conclusions must have been difficult for Robert Hooke. He would have manually calculated his math and observation, which could have led to misinterpretations. 2.3, Experimental process motivation. Robert Hooke's experiment led to Hooke's law, were driven by a combination of intellectual curiosity, a desire to establish fundamental principles, practical engineering, and a collaborative spirit of the scientific community. While his work was intentional and focused on understanding elasticity, it also exemplified the nature of scientific inquiry. 2.4, Experimental process original benefits. The discovery of Hooke's law brought many benefits to the world after being discovered in the 17th century. Hooke's law established a fundamental relationship between force and displacement in elastic materials. Hooke's law allowed engineers and designers to predict the behavior of springs and elastics, improving their designs. Hooke's law became a fundamental concept taught in physics and engineering courses at school, helping generations of students better understand the principles of force, motion, and material behavior. And Hooke's discovery influenced future research into behavior of materials, which would later lead to more advanced theories and studies.
3.1 Modern experimental process. The modern experimental process is typically conducted by attaching various masses to a spring and then measuring the position change. This process facilitates the observation of the linear relationship between the force and displacement. It can also extend into exploration on how changing gravity affects weight applied into springs. 3.2 Differences in the modern approach. Modern day methods for testing Hooke's law may involve analyzing the stress strain relationship in different materials. Some of these materials can be those that wouldn't necessarily fit the description of those of Hooke's law. The original experimental method for Hooke's law essentially focused primarily on the direct relationships between the force and the extension of the springs, while the modern approach puts an emphasis on the theory of elasticity and testing various materials instead of testing only springs. The modern approach also tests these materials at varying deformation points. Another difference between the original and the modern approach is that the original method involved measuring the extension of springs under increasing loads, while the modern method could involve multiple setups. One example would be applying stress to a different type of material and measuring the deformation, or even analyzing various materials under varying load conditions. The testing method for the modern approach is dynamic loading, which means forces are applied suddenly and is also more comprehensive than the original method. 3.3 Modern benefits of discovery. A major benefit is that Hooke's law is essential to engineering, material design, and things such as trampolines. In vehicles, it is used in testing spring-based shock absorbers in the suspension systems. These are designed to absorb the vibrations and shocks from uneven road surfaces, causing the springs to compress and absorb the potential energy from the vehicle. In watches, the balance wheel within the watch or clock is matched with a balance spring. The balance springs are typically made of steel, which would be an elastic, highly elastic material. The balance spring will stretch and contract in tandem with the oscillation of the balance wheel, applying a restoring force, thus ensuring the watch or clock stays on schedule. Hooke's law is even utilized in making and testing of trampolines. Trampoline springs will distort when someone is jumping on the stretchy material. The springs then absorb the kinetic energy and release it, causing the stretchy material to move upward, which then propels the jumper into the air. 3.4 Future research expectations. Hooke's law is widely applicable but still has limitations. Future research is expected to focus on being able to recognize those limitations. The law becomes invalid if a material is stretched past its elasticity, causing permanent deformation of the material. Future research is also expected to continue to explore different materials like those of composites or shape memory alloys. Future research could even integrate modern technology to create computational modeling to provide a better understanding of the behaviors of certain materials and also the approach for complex loading conditions. Relevance of example question to topic. Our question is: a spring has a constant of 250 N over M. If the spring is stretched 0.2 meters from its equilibrium position, what is the force exerted by the spring? Hooke's law states that the force exerted onto a spring is directly proportional to its extension within its elasticity. By finding the force exerted by the spring, this question is directly relevant to Hooke's law to determine whether or not the force exerted is directly proportional. Benefits of understanding the question. The benefits of understanding the question are calculating the force is a direct application of Hooke's law. A practical application benefit include engineering, energy storage, motion prediction, and measurement of force, and a more in-depth conceptual understanding of physics, specifically Hooke's law. Process of writing the question and equation format would be as follows. And the negative at the beginning of the equation indicates that the force is a restoring force and will behave in opposite direction to displacement. Uniqueness of the question. The question details specific parameters. The question is a classic example of the original testing method of Hooke's law. It is self-contained, providing all information needed for the question to be solved within itself. It is direct and concise, straightforward, and immediately presents the necessary information. And the question focuses on the calculation with the primary goal being the elicited calculation.
And 5.1 is our graph based on the question that we had. So this is our graph showing the force um, versus the extension in the Hooke's law. And it's, as you can see, going straight down. So 5.2 is the main formula of Hooke's law,
Sorry.
which is the force. F is force. It is applied to the spring or the elastic object. Force is units like newtons. And then it is also a reasonable range, 0.1 newtons to several hundred newtons, depending on the spring or object being tested. Also note that force use the negative sign means the force is in the object, the opposite direction of the displacement, restoring the force. K in the formula is negative, and it is the spring constant. The units are newtons per meter. What it tells us is the stiffness of the spring. A higher K means the spring is stiffer and harder to stretch. A reasonable range, small springs will be from between 10 to 50 Newton. And then car suspension springs 1,000 to 10,000 Newtons. The X in the formula is displacement or extension or change in the length from the spring's natural length. The units are meters, and the reasonable range would be from 0.001 meters to zero point 0.5, depending on the spring. Constant explanation, there is no universal physical constant in Hooke's law, like in some other formulas, but the spring constant K acts like a constant for any given spring. It's not a universal constant. It changes depending on the material and construction of the spring. The units Newton and meter, which cancels out correctly with the meters of X to give newtons of force. 5.3 step-by-step solution. Step 1 is identifying the known values from the problem. So K is 250 Newton, the spring stiffness or the resistance to the deformation, and X is 0.20 meters, the displacement from the equilibrium. Step 2, you would plug into Hooke's law equation. So substitute the known values into the equation. And then step 3, you would interpret the result. The negative sign in the result, F equals negative 50 Newton, tells us that the force is in the direction opposite to the displacement. Since the spring was stretched to the right, positive direction, the spring pulls back to the left. The magnitude of the force is 50 Newtons. Verifying the solution. So problem 5.3 was a spring with K equals 250 Newton and is stretched by X, which is 0.20 meters. Using Hooke's law, the interpretation would be the spring pulls back with a force of 50 Newtons in the opposite direction of the stretch. So verifying the solution, it is correct, and the conceptual interpretation is aligned with physics principles. This is 6.1. Robert Hooke was best known for Hooke's law. He was versatile in the 17th century he also worked alongside several major figures in the scientific revolution. While Hooke didn't necessarily collaborate in the modern sense on Hooke's law specifically, he was deeply involved in the scientific community and interacted with many prominent scientists. For example, Isaac Newton, Christopher Warren, Robert Boyle, Edmund Halley, and John Wilkins, and other Royal Society members. 6.2 Hooke's Law Group Reflection. What we expected versus what we learned. We expected just the formula, which is F equals negative K multiplied by X. We also learned how it applies to springs, energy, and real materials. What we didn't get to was hands-on material testing and modern uses like in medicine or architect. What we would explore with more time is when Hooke's law stops working, elastic versus plastic deformation, or real world engineering applications. Extra topics that we suggest is scientific rivalries like Hooke's law versus Newton's law and how credit is shared in discoveries. 6.3 Hooke's law summary and project reflection. So the topic overview, Hooke's law explains the relationship between force and the extension or compression of elastic materials, expressed as the formula force equals negative K times X, where K is the spring's constant and X is the displacement. It's a foundational concept in physics, especially in mechanics and material science. Project development process, our group began by researching the background of Hooke law and the discovery of this law. We then explored real life applications through experiments, calculations, and graphing. Each member contribute by handling parts like research, visuals, data collection, or presenting. Collaboration improved as we shared feedback and refined our content. How it went, our project went smoothly overall. We stayed organized and managed to meet deadlines. Some challenges included understanding nonlinear behaviors, but we overcame them by using clear visuals and examples. What was most important about the topic? Understanding how forces affect materials and the limits of elasticity helps us grasp broader physical and engineering concepts. About the project, learning to communicate science clearly, whether through graphs, presentations, or teamwork, was just as important as the content itself. And 6.4 is our relevant sources for our project.